And action. All right. All right, here we go. We were making our way then through the idea of the oxidations and the reductions, and we talked about the oxidations of alcohols last time there, right? So remember, right, within the realm of organic chemistry, what are we looking for with oxidations then? Oxygen, thank you, Sophia, that was good. really narrowed it down there, right? You got it, right? What are we specifically looking for? Formation of bonds to oxygen, right? So whether we're adding bonds to oxygen, right? So that's kind of the definition that we go with there. Now technically, and like I said, remember that what's really at work behind the scenes is the idea of changing the oxidation states. Okay? If you add a chlorine to a carbon atom, that would technically be an oxidation, right? If you remove a hydrogen and add a chlorine there also, right? That would be an oxidation also. And so you guys have been doing this all along, however, within the current context, right? We're adding or removing bonds to oxygen, right? So we talked about the oxidations. We had two broad classes of oxidations, right? We had those that completely oxidize things. So you take a primary alcohol all the way into a carboxylic acid, right? And we typically saw things like transition metals with oxygens, or highly oxidized transition metals in the presence of water, right? That was kind of the way that we could identify whether you're going to completely oxidize something or not. We talked about the other methods that we had without water, where we had PCC and PDC and DMP, right? We talked about all the alphabet soup there that made, or that controlled our oxidations, okay? And then we talked about probably the preferred method there, the Swern oxidation, which was the DMSO and triethylamine and oxalyl chloride is what it is, right? So we have a couple different methods of these controlled oxidations that we discussed. And remember, the other idea was, or kind of always a thing to keep in the back of your mind through the second semester at least, is the selectivity of the functional groups. We talked about primary versus secondary versus tertiary alcohols, and that's the thing to really pay attention to, right? The primaries are the ones that can make aldehydes, right? That's our easier method of making aldehydes now. The secondaries we can turn into ketones, and we're going to learn a lot of ketone chemistry, right? And the tertiaries aren't really going to do anything. We can't oxidize and reduce them, right? So that's the thing to pay attention to with that, okay? From there, we started to launch into this here, which is the reductions, right? And we said that oxidation is adding bonds to oxygen. Reduction is essentially adding bonds to hydrogen or removing bonds to oxygen, right? Either way there. And so the first way that we're going to learn how to do that is this lithium aluminum hydride. We talked about this quite a bit, right? We said that this is a hydride source. It'll reduce the crap out of everything, okay? We're going to talk about it in the context of carbonyls. And it'll pretty much reduce any carbonyl compound that we come into contact with, okay? We're going to talk about aldehydes and ketones now. We're going to come back later and talk about some of these derivatives, and we'll see the exact same mechanism at work, okay? The other thing that we started to mention is that each equivalent of LAH, right? Each equivalent of the lithium aluminum hydride is 4 hydrides. And each of those 4 hydrides are as reactive as the element, right? So each equivalent of lithium aluminum hydride can react 4 times, and we're not really going to stop it, right? You can't really control these reactions. They're very fast, they work very well, and it's just, you're going to reduce it all is what it is, okay? So we can't play any of those games on paper with this is what I'm saying. We can't just say, oh, I'm adding the right number of equivalents just to do 1 reduction. It's going to reduce everything, okay? That's all I'm saying with that. The other thing we talked about is remembering that whenever we do a lithium aluminum hydride, the LAH reduction, that it's under strong basic conditions, okay? Strong basic conditions. And so at the end of it, we're left with that deprotonated oxygen and the deprotonated alcohol. And so to get our alcohol out of it, we have to then come back in and do an acid workup. And we're going to see these acid workups happen again and again and again, okay? Good? I think of this chapter. I didn't introduce the other stuff. That's all right, we can come back to it. Oh no, there it is. Okay. So I'm just making sure I don't miss anything out of the chapter that we're going through here. Now, I'm going to show you guys the exact same thing, okay? Thank you. That's the appropriate level of enthusiasm here, right? Stunned silence. Oh, same thing. Okay. So we could do something like this. So NaBH4. What in the world do you think that's going to do? Yeah?
Well, you said it was going to be very similar, so it would act the same way because the boron has four hydrides around it, so it would reduce everything.
Where's boron on the periodic table?
Next to carbon.
Where's boron on the periodic table?
Second row.
Second row there. What's right below it? Oh, aluminum, interesting. Where's sodium on the periodic table? Right below lithium, huh? Have you seen something that has maybe lithium and aluminum in it? With some hydrides? Have we run into anything like that before? Do you guys get the point that I'm making here? This is just a derivative of LaH, right? Is it different though? Absolutely. Okay, it absolutely is different. Sodium borohydride, right? First of all, the big difference is there's no three-letter abbreviation for it, right? Sucks, this stupid thing. But sodium borohydride here, right, is essentially a derivative of lithium aluminum hydride. It does react different, okay? We would consider this a more mild reducing agent. It will reduce aldehydes and ketones, but it won't reduce some of your other carbonyls, okay? And that's going to be the useful part of this. When we start to learn the reactivity of some of the other carbonyls, we will have to make the decision about whether to use sodium borohydride or lithium aluminum hydride. Lithium aluminum hydride is going to reduce everything. Sodium borohydride, more selective, okay? So we're going to see this come up again later, so I'm telling you. For the moment, it's going to do the same thing, okay? It's going to take this down. It's going to take this down into the appropriate alcohol, okay? Now, if you take a look in the book, what they tell you is that you can do this. Sodium borohydride, and you can use some MEO in there, okay? Now, first of all, what in the world is that? So MEOH is just an abbreviation for methanol, okay? So whatever you want to say for methanol. The point that doesn't necessarily have to be that it's methanol or not, right? It's just you have some kind of mild protic source, okay? There's a couple of things going on behind the scenes. I'm not going to talk about it here. You guys aren't chemistry majors, right? And you guys are biochemistry majors. So a little bit of a different focus for that, right? I'm not avoiding telling you guys important things. I'm just saying, there's some things you guys don't need to know in that sense there, right? But why would it be useful that I could use methanol instead of H3O+? What's basic?
The OH.
Could be, right? What's the point of the acid workup to begin with?
To put back an acidic hydrogen.
Right? So remember, right, the reason why we have to do an acid workup is to protonate the O-. So what do you think the point of the methanol is?
It already has that acidic hydrogen. It has, like, the capability of doing that stuff.
It can, right? It can reprotonate. that O minus there. So who cares? Why would we use methanol then?
Acidic alcohol.
Okay.
It's not acidic.
Got it. How acidic is H3O plus? Pretty darn acidic, right? It's the most acidic we can make something in aqueous solutions, right? That's the leveling effect, right, that you guys talked about in Gen Chem. Yeah, Dr. H, yeah, leveling. You guys remember what the leveling effect is? Right? The leveling effect is, right, if I put sulfuric acid into water, it's going to make H3O plus. If I put hydrochloric acid in the water, it makes H3O plus. Right? It doesn't matter how strong the pKa of your acid is, if you put it in the water, it makes H3O plus, right? Everything ends up making that same strength of acid, right? But with methanol there, right, what's the pKa of methanol? Like 16-ish, right, you know? What's the pKa of H3O plus? Like 1, right, something like that? You guys get what I'm saying with this? Like, alcohols aren't all that acidic, right? It will reprotonate an O minus, right? It'll establish an equilibrium there, right? But H3O plus, will that only react with the O minus? No, it'll react with any other basic group that's on the molecule. So if you have an amine somewhere on your molecule and you add H3O plus, guess what it's going to do? It's going to protonate it, right? H3O plus, you can do hydrolysis on alkenes and alkynes, right? It can do other reactions with other groups on your molecule there. But because of how sodium borohydride works and some of the games we can play with it, you can protonate things by using very, very weak acids like other alcohols. Okay? So that is one benefit that we'll see, and we'll see a couple of other discussions with that come back later. Okay? So remember, like I kind of started off my rambling today there, always pay attention to selectivity. Oftentimes when you're going through OChem 2, we're just like, yeah, and then you do an acid workup, and you guys are like, yeah, acid workup, right there. Okay? But remember what kind of acid you use and the solvents that are used. That's the kind of stuff to start to pay attention to here now. Okay? Cool. If you don't pay attention to solvents, then you might not end up making soap or something like this. I don't know. I'm joking. I feel personally attacked. All right. So now let's talk about something else here, which this is new, but oh, I'm sorry, did I show you guys the mechanism for this? Yeah, I did. Okay. So now let's talk about something that's exactly the same. Okay. Let's do this a different way. All right. Okay. Our good old buddy, alkyl halide, right? What can we do with an alkyl halide? The answer is a lot, right? You can eliminate, you can reduce, you can oxidize, you can turn it into an alcohol now, which can turn it into an aldehyde, right? You can do a ton of things with it, right? We're going to learn something new, and one of the more useful, let's say, ways of doing a certain reaction which we haven't talked too much about yet. Right? So I'm going to ask you guys a question at the end of my ramblings here. So in about 40 minutes, you know me, right? I'm going to finally done talking. I'm going to ask you a question and say, why is this reaction unique? Why have we not seen this before? What is different about this that we haven't really seen before? Okay, you guys ready for that? Now, all you guys are going to pay attention to that. No one actually talks. Okay, so there's a class of compounds called Grignard reactions, is what it is. So it's named after the French chemist. I'm pretty sure he was French. Right? Grignard. Right? And a Grignard is we have to make these reagents, okay? And what I mean by that is this. So Grignard reagents are going to be fairly reactive, okay? So it's kind of difficult to sometimes put these into a bottle and then just throw wherever we want, right? They tend to react very easily with moisture in the air, and given time they'll start to decompose and this kind of stuff, right? So a lot of times what we would say is we make a Grignard in situ, right? If you guys have seen that in the book there. We make it as we need it, right? So if you ever hear me say that term or whatever, that's what I'm talking about. I'm asking you to make something and use it in the solution, right? So we make something in situ is what it is with that, right? Now to make a Grignard, we have to start out with an alkyl halide, okay? And we take that alkyl halide and we throw some magnesium in there, okay? We typically take an excess of magnesium. So in the book, you'll see 2 equivalents, okay? Or you'll just see excess or anything like that, okay? And this is just solid magnesium. And we used to do this experiment. We might end up doing it this semester. There's just, well, anyway, I don't need to ramble about this. So anyway, so we'll see if we'll end up doing this or not. It didn't work last time I did it with my students. That's why, right? And you guys couldn't even make benzocaine. No, I'm joking, right? But so like I said, this actually is a very common procedure. We usually end up doing it, but I couldn't figure out why the last class we couldn't do it there. So that's why I don't want to give you guys an experiment that doesn't work, right? Because what's the point then? We just have you guys run in circles for 3 hours. And, right, okay, we're back where we started, right? You know, if the experiment doesn't work, you're back where you started anyway, right? But anyway, so what we would do is take an alkyl halide, you just get magnesium shavings, and you have to kind of grind them up a little bit because they oxidize on the surface, and you dump them into your alkyl halide. And then sometimes you have to add a little bit of a catalyst to it. So sometimes you'll see it with an I2 there at the bottom or something like that. It's not too important, okay? I'm just giving you guys something in case you might see it, right? That's all it is. What happens then is a series of radical reactions where at the end of the day, we end up making this, okay? So we have a carbon bound to the magnesium, and the magnesium is bound to the bromine, okay? Now, Gen Chem question. What is magnesium? I heard the second part of that. It is a metal. it's in your S block, right? Remember your transition metals are your D block, right? But magnesium is a metal. And it's bound to a carbon. What is carbon? A non-metal. What do we call it when you have a non-metal bound to a metal? An ionic compound. Got it? This is important. Because what do we know then about ionic compounds? You have a cationic part, a positive part, right? And you have a negative part. You guys with me on this? Which part is the negative in an ionic compound? The non-metal is. Which one's the cation then? The metal. You guys got it? You guys understand what I'm telling you? Okay, so what does that mean here?
It's an ionic compound.
You know what? Annie, you nailed it. Like she was looking at that pitch the whole way, right? All right, you are correct. It is an ionic compound. You're absolutely correct. What else does it tell you? What else does it tell you then?
Carbon has a partial negative.
I would say almost correct. Correct. Amend your statement a little bit there. Carbon has a so we said it's ionic, right? The non-metal has a negative charge, and you told me carbon then should have a negative charge, right? The distinction here is whether it's a full negative or a partial negative, okay? For our purposes, and whenever you see this kind of written in the books, and carbon has a full negative charge, okay? What's step number 1 whenever you guys are assessing a mechanism? Find your negatives and find your positives. You guys with me on this? That carbon right there, doesn't look like it, but this is an ionic compound. That carbon is a full negative charge. So oftentimes when you guys see me work with Grignards or whatever in the mechanisms, you'll just see me kind of just draw like this with a carbon with a lone pair and a negative charge on it, okay? Or if we have some kind of longer alkyl chain, you'll just see me put a negative charge like that, okay? Why do we care about that? Well, remember the cation is just going to be spectating in this case, the magnesium part there, okay? And the carbon with a negative charge is the one that's going to be doing the work. Sound good? Okay. Now let me continue. That looks like a kind of a smiley face, right? There we go. All right, there we go. Okay. So, angry carbon. So, question. What do we know about a carbon with a negative charge? How many times have we run into that? Be very careful. How many times have we run into that? Once. Close. All right, I think so far we've only run into it once. All right, if we have run into it twice, I'm sorry. I can only think of one at the moment, though. Okay? You guys remember where else we've seen a carbon with a negative charge? It's a very special case.
Resin structures?
Aha, okay, so in resin structures we see negative charges get delocalized. That's true. Well, we've actually made carbons with negative charges as part of our reactions. I remember where we've seen that before. So what is the product of this reaction? That can happen. That can happen. There's another, that would be a minor product. We'll use a major product in this case. So you're having this act as a nucleus. Really small case. Right? So what would happen if you would approach it from that side? Or with that line? Tell me, what's the product of this? What functional group gets made?
That's okay.
She could have the glory, right? But Jerry, both of you guys are absolutely correct, right? So we end up making an alkyne here, right? So we end up doing this. Let me just double check because I have a tendency with alkynes to kind of drop carbon sometimes, right? So I always go back and double check myself. Good. So this is our method of making an alkyne, right? The sodium amide, the NaNH2 in ammonia, right? We'll end up doing two E2 reactions on those dihalides there, right? And we end up making an alkyne. Good. Okay. Well, Do you guys see a carbon with a negative charge? Me neither, right? But if we play the same game here, okay, right? The product that we end up making is, let me draw this a little bit differently. 1, 2, 3. Telling you, okay. There it is, okay. 1, 2, 3, 4. Okay. We end up making that right there. Quick question. We have a carbon with a lone pair and a negative charge. Now, if you remember when we started to discuss this reaction in the first semester, we talked about acidity of the CH bonds, right? This is a terminal alkyne that has a pKa of about 25, okay? If we had a hydrogen there, right, where the negative charge is, right, that would have a pKa of about 25. Not that acidic at all, but when we have a really powerful base, like the sodium amide, right, then it's going to easily deprotonate that. And now we have a carbon with a lone pair and a negative charge. Now, what do we know about carbons with lone pairs and negative charges? If they have a pKa of 25, which is a garbage acid, that means they make what? Really strong bases, right? Really strong bases. So here we have a strong base, and it happens to be a good nucleophile, right? And so we can do SN2 and E2 reactions with it. You guys with me on that one? Yes? So question, okay? All that was to go back and ask you guys the exact same question and say, look, now we have a carbon with a negative charge. What do you guys know about carbons with negative charges? They're really strong bases, yeah? Now, what's the difference here? The difference here is essentially we have not an alkyne carbon, right? This is an sp3 hybridized carbon that's deprotonated. What's the pKa of its conjugate acid? What's the pKa of an alkane? Remember that? It's about 50. Okay? So a pKa of 50, what does that mean to you guys? It's not an acid at all, right? It's not acidic in any way. Right? It's not acidic in any way. But here we have the conjugate base for an alkane. What do you guys know about that base then? It is ridiculously powerful, right? Remember, the weaker the acid, the stronger the base. Got it? And if you have a pKa of 50 and now you're deprotonated, you're going to be going after any and every hydrogen there is. Okay? And in fact, that's why they're so useful for us. They're extremely powerful bases. And they're pretty cheap to make too. Magnesium's cheap, and a lot of these starting alkyl halides are cheap to make, right? So they're extremely powerful bases. But they're also pretty darn good nucleophiles. Okay? You guys with me on this one? You guys know what I'm about to ask? Yeah, I think I got it, Dr. H. So here's my question. Let's say I take a Grignard, right there, okay? Why don't you guys see if you can come up with what do you think the product is going to be for this? So find your negatives, find your positives, right? Where's your negative on one atom? The carbon, right? So why did you put the positive and attach the positive? Do you get what I'm saying? Yeah. Close. Okay? So this won't be there anymore. Yeah, but so this is an ionic compound, so we can just separate those two out and just use the instructions. Okay? I'll tell you what happens to the other in just a second. So it's not, you're not technically wrong, that it's not going, this isn't going to be there, it's actually going to be up here, but that's what the negative is now, okay? I like that, right? So you have, when you do that, what charge is left on that carbon here?
This one is
Down. A positive, right? So now you know where your positive is and what's the charge in that carbon. So what do you need to do with that? Got it? Where's your positive and negative? Right? Oxygen's always going to be what? Negative. So why'd you put a negative onto the negative? Huh? No, I'm asking a question, right? This is negative, and you put a negative onto it.
Oh.
You see what I'm saying? Yeah.
Does it go after?
What do you think? Organic chemistry is the chemistry of carbon. Does that answer your question? What's a pi bond made out of? Electrons. Would a negative go after a negative? Good question. So remember, when you guys see this, here's what you guys are seeing, right? You're seeing a carbon with a lone pair in the negative charge there, right? You guys with me on this? Remember, these are ionic compounds, so we can separate the negative and the positives out. So now I know where my negative is. Where's my positive? My positive is going to be here, okay? That red carbon. That red carbon, which is called what? I don't know. Remember that red carbon is called our carbonyl carbon. Right? I know we talked about that way back in the day when we first talked about functional groups. But that is our carbonyl carbon. So the carbon that's involved in the double bond with the oxygen. You'll start to hear me call that the carbonyl carbon. Guess how the carbonyl carbon feels? Positive. When will it ever not feel positive? The answer is, when will it ever not feel positive? That's poor grammar. No. when will that have a different charge? The answer is, it won't. It's always going to be feeling partially positive. You guys with me on this? Do you understand why that's important? Because whenever you have a carbonyl group, aldehyde, ketone, ester, all these other groups that we'll talk about, that carbonyl carbon is feeling partially positive. So guess what's going to happen? Something negative is going to attack something positive. You guys understand what I'm saying? So guess what's going to happen in all of the carbonyl chemistry? Something negative is going to find that carbonyl carbon. So I just taught you guys 3 chapters in the book, and that statement right there, literally that's it. Okay? You guys want to take a couple days off? It's just the first week, guys are like, I'm sick of it. Right? But no, that's seriously what it is. So always keep in mind that carbonyl carbon there. Okay? Because remember, what's kind of our statement? Every time you make a bond, you have to break a bond, right? And you'll notice we got a pi bond there, right? So we're going to make a bond to the carbonyl carbon, and we kick up that pi bond. Does this look familiar to what we just talked about with our hydride reductions? Absolutely. Okay? Absolutely. So what's our product here then? Here's where we have to be careful again. Let's see, red for negative charge. On here to our 2 green carbons. Here's one of the problems. This is a place where you guys start to go in the carbon diet. Do you know what the carbon diet is? It happens in the second semester of OChem. You guys come back from the holidays, Thanksgiving happened, Christmas meal, right? Got candies for Christmas, and oh man, we're in Florida, I gotta get my beach bod back, right? So you gotta start trimming the fat, right? And what do you guys do? You start dropping carbons. You go on the carbon diet. Don't lose carbons. Okay? Always go back and double check and count your carbons. You see me do it, right? It's not that I'm like, this is, unless that's how I make mistakes, if I don't go back and check myself, right? So make sure you have the right number of carbons in the products there, okay? Yeah?
Can you explain why it's partially positive? Is it because of like the...
What's partially positive?
The carbon?
The carbonyl carbon? Great question. Why is the carbonyl carbon partially positive? Not the double bond, the oxygen, right? So this is an instance of a dipole, right? The electronegative oxygen is pulling electron density away from that carbonyl carbon there. What's another reason why we know it has to be positive? Dominic, you had it down on your paper. What was it? The first thing you drew on your paper when I came by there. Perfect, right? There's a resonance structure that we can draw, okay? So if you think about this, can you guys draw a resonance structure for this? Sure, right? You would draw this, and we would end up with a resonance structure that looks like that, right? Is that a good resonance structure? Not really, right? But is it a valid resonance structure? Yes, it is, okay? You guys with me on that? So there's two good reasons why the carbonyl carbon is positive. Electronegativity and then resonance. Got it? Good question. Okay, you guys ready to think? One person said yes, the rest of you guys don't have a choice now. All right. How much do you guys want to think? A little bit or a lot? Scale of 1 to 10, give me a number. Surprise us. All right, you guys got it. I'm going for a 10. I'm just kidding. No, let's try a little bit easier first. Okay, then we'll ramp it up here. But I want you guys to think. Okay, I want you guys to think. Oh, I'm sorry, before I have you guys think. Sorry. All right. So what do you guys notice about the product currently? Oxygen has a negative charge. So how do we have to typically finish up our Grignards? Acid workup, right? So put some H3O plus there at the end, and then we end up at the same pronated alcohol as our product, right? So the mechanism is identical, right? The mechanism is identical to what we see with the hydride reductions. But what's special about this reaction that we don't see too often? What bond did we make? What's our red bond that we made there? A carbon-carbon bond. How many carbon-carbon bonds have we made so far? The answer is not too many, right? Do you guys see why this is such a useful reaction? The reason why it's a useful reaction is because now we can start to build bigger molecules together. Okay? I can have one molecule that I do all my transformations on, and I have another one, and if I make the right Grignard conditions, I can bring those two together. Okay? But we have to be careful, because Grignards are powerful bases and powerful nucleophiles. They're not selective at all. Okay? They're going to go after anything with a positive charge. Okay? But under the right conditions, extremely useful. Okay? All right. So let's think here a little bit. Now we've got an aldehyde. Okay? Okay. All right. What can you guys come up with? to trick you guys. I like the idea. There's an interesting thought behind that, but not in this case. I'm not trying to trick you guys. An interesting thought again, but not what's going to happen in this case. I didn't mean for this to be that tricky. I'm sorry. This is just an aldehyde. That hydrogen there is not that acidic. Aldehyde hydrogens are not that acidic. Now the question might be why, right? Why are they not that acidic? So where's our positive in this case? I'll give you a hint. There's this thing called a carbonyl carbon. Okay? Now to be fair, maybe like I said, maybe I oversold it. Sorry about that, right? The aldehyde hydrogens are not that acidic. Well, we still got a carbonyl group, that means we still got a positive, partially positive carbonyl carbon, right? And we've got a strong base and a strong nucleophile there with our Grignard, so what's going to happen in terms of the reaction? The exact same thing, right? Dr. H, why did you show me this thing? I already know this 100%, right? Quit wasting my time, man. All right. Go ahead and take us to the end here, right? We'll go ahead and do the acid workup and all that. And let's see, this is in red. Oops, red. This is in blue. Are you with me on this? I'll just do this so we can compare the two. Why did I bother showing this to you guys? What's different about my two products? That could be extremely useful for us to pay attention to. What is different in my two products?
This is a secondary alcohol.
See that? Ketones will end up becoming tertiary alcohols, okay? And aldehydes will end up becoming secondary. Okay? Good. Yeah, we'll do that. Now, Grignards basically have a twin brother. And the twin brother for Grignards, we call them organolithiums. Okay, now the way an organolithium works is going to be very similar to a Grignard. For our purposes, we're going to treat them as the same, although there are differences in here. Okay? Now, organolithium is going to start out the same way. We start out with an alkyl halide, and instead of adding in magnesium, we add in lithium. Again, an excess of it. Okay? And what we end up making at the end of this is we end up swapping the bond from the bromine to a lithium, and we end up making the lithium bromide, which kind of falls out of solution, is what it is. Okay? So we don't care about the lithium bromide. I'm just saying that we need more than one equivalent in there. Okay? For our purposes, all we really need to show is this part here, and that's just fine, okay? So we start out with an alkyl halide, we add lithium into it, and then we end up making an organolithium compound. I could walk through the same litany of questions with you guys. What is lithium? And then we'd say a transition metal, right? I'd say no, right? Good, right? So all joking aside, right? Lithium's a metal, carbon is a non-metal. So what do we notice about organolithiums here? They're again ionic compounds, which means our negative charge is where? On the carbon. How is a carbon with a negative charge going to behave? Like a nucleophile and like a base. Got it? Now we're going to see organolithiums come up again later towards the end of the semester when we talk about coupling reactions. Okay? But for the moment, they're going to behave the same way as Grignard reagents for us. Powerful bases, powerful nucleophiles. Okay? Now, I've shown you guys just primary alkyl halides turning into organolithiums or transition metal, let's try this one more time. I've only shown you primary halides turning into organolithiums or Grignards. It's not restricted to primary halides. You can do it with any halide, primary, secondary, or tertiary. And even aryl halides do this. Okay? So your question is, well, it's an aryl halide, right? Good question. An aryl halide, or an aryl group, right? So A-R-Y-L, aryl, right? Is just something coming off of a benzene ring, okay? So if I have this, okay, I can actually start to react that ring. Because if I take this and I add in some lithium, right, I will turn this in to this right here, okay? Does the carbon on the ring still have a negative charge? Yes, it's still an ionic compound, we still have a metal bound to a non-metal, blah, 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 right? That carbon still has a negative charge. How's it going to behave? Like a powerful base and like a powerful nucleophile, got it? It's not going to behave any differently just because it's in the area on the benzene ring. I'm just telling you now we can start to see some of the reactivity coming out. Okay? So what would happen if I put that organolithium in with a ketone? Right? What if I took this and then went on to react it with my ketone there? The same thing, right? You guys with me on that? Right, we'd end up adding that benzene ring to the carbonyl carbon. We'd go through, do our acid work, and adding that together. All the same thing. Good? So whenever we start to make larger compounds, we start to make carbon-carbon bonds, now we've got a good method of doing that. We start from an alkyl halide, which you guys know how to make, right? And then we throw in magnesium or lithium to make the organolithium or the Grignard, and then we can put in a carbonyl and start to clip together larger molecules. Okay? Yep.
What would the product be for that?
Good question. I want you guys to see if you get it. Yeah, I know, but I'm just saying, make sure when you put that like on the or something, make sure you split it up. Right? Good? Not going to behave any different, just maybe it looks a little bit weird or whatever, right? But there it is. Alrighty. And don't forget to always finish it up with an acid workup or a water workup. Water workup works pretty well for these, it's typically what we do. Now your question might be, well, why acid, why water, why these? There's different ways of protonating that alcohol. That's all it comes down to. Right? It depends on what else is in the reaction and these kind of things. Okay? But acid workups just fine here. Good? Got it? All right, I think that's a pretty good stuff before we kind of move on into the next big chunk there. Right? So I will see you guys on Monday then. Don't forget, as we're kind of just finished lab, next week we're going to be going through starting the first part of the raspberry synthesis there. I think there's 2 parts to it, right? So we're going to be trying to go through the first part. So if you guys want to start reading through that and watch the video on the TLC and that kind of thing, you have the weekend off there. Yeah.
Video for the gas.
Hang on to that thought. Good question. Thank you for reminding me. So don't worry about the GC yet. I gotta see if I can get it up and running for you guys. Basically, I'd love to do it. It's a cool little instrument and it's useful in a lot of different fields. But I gotta see if it's working. So I will let you guys know. I'm not gonna surprise. It's GC day. Why didn't you guys watch it? Right? I'll let you guys know ahead of time. But so hang on to that for just a minute. But remember, we are still going to be doing MR and IR. So go back and review those if you guys don't remember how to do it. Okay. Cool. All right. See you guys on Monday.